So today what I'm going to do is talk about some of the things that we've been investing in inside of CoreOS, things that have made it inside of Tectonic, and then walk through where we'd like to see some of these investments go over time. Right. So there's 4 major categories that I'm going to kind of cover here today. First is places that we're investing to make Kubernetes scale better. Establishing identity inside of the cluster, so whether that be machine identity or identity of the users that have access to the cluster. Creating standards for containers, so image formats, how containers actually get built and shipped. And then the last bit is how we'd like to see the increase of Kubernetes use overall, not just Tectonic, but the overall health of the Kubernetes ecosystem. So this is kind of a meme that's been going around, is that like Kubernetes doesn't scale. Part of this was because of a blog post early on that had very modest scaling goals for Kubernetes 1.0. So I just want to kind of break this meme down. Kubernetes scales, it scales quite well. So if you want to take any photos for Twitter, this would be a great one to take. But don't take this next one, because this is work in progress. There's a lot of things that we can do better as far as making Kubernetes scale. So the initial focus of our Kubernetes scaling work begins in the scheduler throughput. This is an important piece of making sure that when you tell Kubernetes that you want to have something running, that it actually effectively gets that thing running in a reasonable amount of time. Increasing and overall just the scheduler performance. So not just throughput, but how much CPU and memory it consumes. And then overall, the runtime overhead. So what is the overhead of containers running on top of that system? How much overhead is there when the kubelet is sitting there monitoring those containers? So one point here, one little proof point that we're on the road to really good throughput inside of Kubernetes is Xiang and Han Chao from our team recently put up a fix to the scheduler that doubled the scheduler performance. And so I think just by going through and doing a lot of fine-grained benchmarking, we can do a lot better inside of Kubernetes. And there's a lot of low-hanging fruit where we're able to get this Kubernetes scheduler scaling up to thousands and tens of thousands of hosts over the coming months. Now, the next piece of scheduling is actually the consensus data store that Kubernetes uses. So for a lot of folks, consensus is a new concept, a concept that a lot of us aren't familiar with. So really what it comes down to is just getting machines to agree with each other. And this is kind of seen as a hard problem for distributed systems. And we know this is a hard problem. How many people traveled for the Thanksgiving holiday to visit family? Yeah? Yeah. Who came to consensus on a political problem with your family? Anybody? No. So consensus is a hard problem. And it's a hard problem inside of distributed systems also. So a consensus store has the goals of storing really critical data, replicating that data between machines, and then providing distributed lock mechanics so that you can have multiple machines coordinating over some data. And then the challenge here is actually recovering from machine failures. Now, inside of Google, there's this system called Chubby. It is used to coordinate a bunch of distributed systems. It's kind of at the heart of a lot of the systems inside of Google. etcd is a data store that we built, and it's at the heart of Kubernetes. It's what Kubernetes uses to persist all of its data. So Kubernetes itself doesn't really hold on to any persistent data, and this allows for really nice horizontal scaling of the API, and then also leader election in case of failure. So if Kubernetes machines go down, they can coordinate through etcd to recover and continue work through the scheduler and through the control plane. So etcd is this pretty critical consensus component that is originally introduced and built by CoreOS, and that it's found a pretty critical place and role inside of Kubernetes. So one of the things that we'd like to do is to ensure that etcd continues to support Kubernetes well, and that it helps in this overall goal of making sure that Kubernetes scales. So some things that we're doing here in the next year, like early next year, is we're introducing a new efficient gRPC protocol for etcd. So this will reduce the memory and CPU complexity of communicating with etcd. We're adding multi-key transactions, which is a feature that the Kubernetes team has been asking for over time. So being able to update and manipulate multiple things in the data store at once. We're increasing the length of history. For a lot of people, they want to use etcd as a way of figuring out what happened inside of the cluster, what changes were made over time, and they want to kind of use that capability of watching for changes to trigger events inside of different components inside of Kubernetes. And so we're working on the data store to increase that event history and also have better memory efficiency overall. So the overall future outcomes from the Kubernetes work that we're doing is we want to see essentially improved utilization and application density through improved work inside of the scheduler itself. We want to ensure that throughput and the overall process from user intention to scheduled pod on a running machine works well and scales to hundreds of thousands of pods and beyond. And that we have the capability for users who set up a Kubernetes host, set up a Tectonic cluster, to understand what is the performance of that cluster going to be, having benchmarks so that they can run that against their system and understand what the capabilities will be over time. So that's the work that we're doing and where we're investing on scaling of Kubernetes and Tectonic. And the overall thing is we want to establish that Kubernetes is a high-scaled distributed system kernel for these applications. Now, yesterday, Alex talked about this concept of distributed trusted computing. And the idea here is that only software your company wants to run will actually be allowed to run on your systems. And it's going to be running on systems that your team controls. This is a pretty challenging problem, actually. So we all know that people come and go, machines come and go, and so you have to build software that's able to handle the ever-changing environment of your teams, and you need to have software that does this in an effective way. So we're all kind of familiar with what's jokingly called in industry as this NASCAR login screen. It's called NASCAR because it's usually just filled with logos. Log in with Twitter, log in with Facebook, log in with Tumblr. And so this whole technology of these login screens is built on some standards called OpenID Connect and OAuth 2. And so we've built an open source OpenID Connect and OAuth 2 provider called DEX that backs the identity services inside of Tectonic. It's open source software. It's built on top of these web standards that are pretty ubiquitous today. We've done work to integrate DEX with Kubernetes, so Kubernetes can actually consume and identify users based on OpenID Connect identities, and it uses a bunch of cryptographic best practices. As we know, people leave teams, people join teams, and you want to make sure that when people leave, we can actually expire those identities over time. And so DEX does things like cycling short-lived keys inside of the database that are used for signing those identities. So some future work here. DEX isn't done, but it is providing kind of a solid base for identity, user identity inside of these clusters. One of the major things is adding groups. A lot of people want to organize people into teams, whether those are administrative teams for the entire cluster or administrative teams for individual applications, et cetera. So we're adding that capability into DEX soon. We have already gotten some pull requests from the open source community for backing DEX with existing directories, existing directory IDs like LDAP, et cetera. We're looking to have DEX certified by the OpenID Connect standards and communities. And finally, we want to make it really trivial for people who have applications that don't have any sort of identity or authentication control to back their application with DEX. So whether that be a monitoring system, some sort of internal tooling, et cetera, we want to make it really easy for the Kubernetes community to take a pod that's unsecured and put a proxy or some way in front of it to protect it and let teams have access to that application. Now, the other challenging part, not just user identity, is server identity. Servers that are able to talk to Kubernetes, talk to the API server, have access to our secrets, et cetera, and will actually be running our application. So we need to trust those also. So there's the dual problem of actually identity, so giving a machine an identity. We understand how human beings have identities, but systems are a little bit more complex, whether that be through a TPM or some sort of generated cert when the machine comes up. You need to establish that identity and then admit that identity into your cluster. And so in this example, say we have a 3-machine cluster. When those machines come up, they're initially untrusted machines. There's really no established identity in the Kubernetes API between that and the node itself. But over time, the system administrator can say, yes, I trust this because I talked to my cloud API service, or I trust this because the TPM signed something, or I trust this because I know that this machine was brought on through the hardware database that we got from our hardware vendor, and we racked that machine. And so over time, essentially establishing those identities and admitting them. And then really importantly, say booting machines out of the cluster in case of that machine getting compromised or that machine being decommissioned and sent off to recycling. So this overall process is something that is in progress. We're pushing a lot of these changes up into Kubernetes so that we're able to create and have trust from the API to the server, to the individual nodes, and the nodes to the server. And so the overall goal is just to establish a distributed system with strong cryptographic trust between hosts and users that are operating those hosts. So the next piece that I wanted to talk about today was around containers and container images and the life cycle of containers. So there's some discrete things that we do with containers. First, we build them. So the Docker file is a really great way in how a lot of people have gotten into building container images. Then you distribute them, download them over the internet, run them under a container runtime, and then do this ongoing process of auditing those container images. And what we'd like to do is build the standard software container. And a standard software container to support that whole life cycle has a number of things. It's an image format, so something that you actually transform your code into, essentially tarball. It has naming and discovery, so that we are able to put configuration data somewhere and say, I want to download this thing. It's called example.com/app. There's the actual runtime itself, so how an application person who's developing their app, what they can expect when their application is running in a container, and then the actual identity and signing. So how do we take a container and generate a cryptographic identity and hopefully sign it by one of our developers so that we have trust that that container is what we expected. We've seen this image 1,001 times over the last 2 years. This idea that we're building the standard shipping container. And I think that we're kind of doing a disservice because we really haven't done that yet. We've been talking about the standard shipping container, which is this ubiquitous thing that anyone can manufacture. It's well understood. There's specifications on what you have to do in order to be the standard shipping container. But we really haven't adopted one as a standard across the industry yet. And so a year ago, we started on this journey with a standard called AppC, where we wanted to essentially work with a bunch of other people in the ecosystem and figure out what is the standard software shipping container. And so writing down those standards, figuring out in very specific language what it means to be a software container. And our goals here were pretty straightforward. We wanted to first enable people to experiment with new build systems. So the Docker file is a great place to get started, but as we know, it can lead to extremely large images. You have these multi-Docker file pipelines. It can lead to a lot of complexity. And over the last year, we've seen a lot of interesting new build systems come out using AppC. So there are things that are based on Debian, but there's also things that are based on interesting new build systems like NixOS. And so I think having this experimentation will get us to a point where we're able to build more secure, more trimmed down containers. We wanted to support people and use cases a lot of enterprises have for having fully air-gapped containers. A lot of the container runtimes today and systems assume that I'm going to be able to have egress traffic off to the internet. And I think we can do better than that, and I think that we can copy a lot of the mirroring practices that we've had from the Linux distros for a long time. And that's one of the goals that we had in mind with AppC. We wanted to enable the creation of new container runtimes. So there's a lot of places I think that we can innovate inside of the runtimes themselves. One of those places that Intel recently did was by adding clear container support, essentially the idea of using a hypervisor to protect the host system from the container application. So there's a lot of innovation that we can do inside the runtimes themselves. And by having the standard shipping container, we essentially are able to say, we don't care whether it's a boat or a train, it's the same thing. The software will run the same way. And the software running the same way is actually why you want to do this in the first place, because it's the application writers that are actually consuming these specs, right? It's easy for us as people developing runtimes to run a bunch of different container formats, but at the end of the day, what people building applications care about is they care about if I package my app today in a container, I want to ensure that it'll run in the same way 3 years from now, 10 years from now. And that's the promise that we actually have to keep as an industry of folks that are trying to get containers in a place where they're ubiquitous and used everywhere. So what's happened over the last year is that AppC has developed as a set of specifications that goes from image format, naming and discovery, runtime, and signing. And then also, we've joined forces with a number of industry partners on AppC. So we have engineers that are working from a number of different companies like Red Hat and Google that are maintainers on the AppC thing. And then a few months ago, earlier this year, we joined with Docker and a bunch of other folks to establish the OCI, which is the Open Container Initiative. And what the Open Container Initiative has done is it's scoped itself to the point where it's only tackling the runtime side. So what, as an application writer, can you expect to exist when you launch the container? So it doesn't cover the image format or naming and discovery or signing, which I would argue are pretty critical pieces of this whole thing. Containers are only interesting because you're able to pull them over the internet. So there's opportunity here that AppC and OCI share kind of a runtime spec, but there's a lot that needs to be covered still inside of this specification that we're driving for. Now, as an example of why kind of the last bit of this life cycle, besides just the standard of the shipping container, why the last bit of the life cycle, which is ongoing auditing, is important. Alex talked about this yesterday, where inside of our Quay.io product, we have a scanning service that walks through and looks for vulnerabilities inside of containers. And what we found is that there's a lot of vulnerabilities inside of these container images. And so in order to enable that technology of actually scanning these images, what we've done is we've open sourced a project called Clair, and it goes through and audits these containers. And the way that technology works is that we have a container image format. Inside of a container image is your actual application and whatever software was installed when you built that container. And then a lot of container images today have some sort of metadata about what software was installed in there, whether that came from Debian or Fedora, et cetera. And so what Clair does and what we do inside of Quay is we take that metadata and we figure out if there are vulnerabilities in installed packages inside of that container. It's a pretty straightforward process, and I think there's a lot of opportunities for this last bit, this audit part of the container lifecycle, to be doing more interesting work for a lot of us. The most important thing is that I think we can be adding more and more data sources. So right now we're going and parsing out Debian and Fedora information, but there's a lot of places that we get software besides just the Linux distros and Linux package management. We have things like Maven, we have things like PyPy, we have just NPM, essentially a large number of sources where we get libraries that our software relies on. One of the great things about open sourcing Clair is that we can imagine this auditing not just happening inside the registry, but being an ongoing process inside of our cluster, where Clair is actually looking and seeing what copies of containers are running in the cluster, and are any of those vulnerable? If they are, be paging people who are administrating that cluster. And I think one great outcome would be for us to create a standard where we can have a really minimal set of metadata. not just going through and parsing this existing metadata where we're getting it from Fedora or Debian, et cetera, but having just a really small file that people are able to place on disk, kind of a standard file that describes what version of XYZ library is in this container and what are the dependencies there, so that we can find this information without kind of rooting around inside the container itself. All right, so the overall goal here is that we want to see software containers as standards so that people, developers, can build and ship their applications confidently and have a long runway on that application continuing to work. And there's a lot of moving parts there to achieve that goal. Now, the last kind of goal that we've been investing in is enabling Kubernetes as a framework of distributed systems that is widely adopted. And a couple of places where we've been investing most heavily is inside of networking and the actual onboarding process for Kubernetes. So as we know, Kubernetes has this networking model where every single pod gets its own IP address. This causes a lot of scariness for a lot of people because they now have this sort of complex network that they need to deal with. But the reason that Kubernetes did this was that it is less complex for the application developer to have a very consistent IP address that they're going to get. It makes things like DNS work by default. And application developers can rely on the same IP inside of their container to be the one they have outside that they can actually be addressed at. Now, obviously, as I mentioned, the challenge is that having multiple IPs for an individual machine or individual host is a challenge in many networks. And so what we've built and what our goal has been with Flannel, which is a easy-to-use kind of default option for networking inside of Kubernetes, is that we want to take a world where a lot of us exist today, where we're inside of a virtualization environment or we're on some sort of physical network where one server gets one IP address, pretty common case. And we want to map it to this world where Kubernetes has one IP address per application, essentially. And so what we do is we coordinate and create an overlay network where that actually happens, where we're able to map from one IP address that's understood on the overall network and create an overlay network on top of that for Kubernetes use. And this whole thing is orchestrated through etcd and uses Flannel as the way of actually orchestrating that work. So what we wanted to do and why we built Flannel is we wanted a reasonable default. We don't think that Flannel solves all the problems, but it's a pretty straightforward IPv4 overlay. Yesterday, we got a lot of people excited, or a lot of people were excited about, scrap IPv4, let's just use IPv6. And that was actually one of the things that we initially thought about was just, well, forget about it. Flannel doesn't have to be anything more than a way of advertising the IPv4 addresses, and then we'll just use IPv6 subnetting. Unfortunately, many applications are very unhappy about IPv6. So for the time being, Flannel is a pretty good stopgap solution. Now, I'm not going to claim that Flannel solves all the problems. And we have a lot of people who are solving the Kubernetes problem of networking in various useful ways that integrate with existing hardware, that provide insight into how the network is communicating, provide access control, et cetera. And so we've built a thing called Container Networking Interface that is now part of Kubernetes. And it's a simple network plugin interface that's being adopted by a number of vendors. Metaswitch Networks, Project Calico has a CNI plugin now. Weave works as a CNI plugin. We've added a bunch of CNI plugins for very common network protocols also. And so our goal here is essentially to make it really easy for Kubernetes to plug into existing networking control planes. It's super unopinionated. It's very straightforward, simple interface. We've engaged, like I said, with a lot of the network ecosystem. These vendors that have already built CNI plugins, we've gotten a lot of feedback from engineers at Cisco and some of the other larger vendors also. And it's most importantly been adopted inside of Rocket and then also inside of Kubernetes. So we're on the path to essentially having a single ubiquitous plugin interface for networking inside of Kubernetes and other container runtimes. So the future here for Flannel, we are in a pretty good spot. Flannel is a solid IPv4 overlay networking system. We are planning on adding really simple IPsec also, so that you can have end-to-end encryption on the overlay network. For the CNI, we're going to continue to work with network vendors to ensure that CNI gets adopted and that it is the sane, reasonable default inside of Kubernetes for network setup and orchestration. And we'd like to essentially, as we get to this point where we have more and more people using the specification, we want to get to this point where we have our first initial release of the spec and we kind of just settle it down. As I mentioned, the spec's very straightforward and simple, and there's not really a lot of moving parts. So I think we'll be able to do this early next year. And finally, just get it promoted as the default plugin system inside of Kubernetes for networking. Now, the last couple of bits on increasing overall adoption, Kubernetes is often seen as something that's kind of difficult to get up and running. We're tackling this in a few different ways. The first is just by starting and writing and building a lot of documentation and tooling around Kubernetes to make bootstrapping really straightforward and easy. And then the other piece that I've heard and we've started to build documentation around is just how do I recover? There are a lot of moving parts in Kubernetes, and this is for a good reason. It allows for separation of concerns, and it allows for really easy recovery in cases of disaster. There are very clear boundaries of where state is stored and then where things are stateless. And so there's a lot of places where we can continue to improve this story and just show people who are having to administer these clusters, how do I upgrade it? How do I recover from backup? What happens when something goes wrong? So our overall goal is just to ensure that Kubernetes is adopted and that it has all the infrastructure around it to be successful. Now, the final thing I wanted to talk about today was the Cloud Native Computing Foundation. So the Cloud Native Computing Foundation brings together a bunch of different industry partners who are interested in the overall success of this cloud native idea. In particular, it starts with Kubernetes and the Kubernetes IP being donated to the foundation. And so there's a few things as we go into the first Cloud Native Computing Foundation board meeting that we as CoreOS intend to propose. First is that we intend to donate AppC into the CNCF and continue to develop, and we'd like to see essentially that continue to develop as a shared software container standard. We think that there's a lot of useful work that can be done here, and overall that we can continue to invest and see the container format, the distribution and naming be something that can be shared across multiple systems. We intend to donate critical pieces of software that are inside of the Kubernetes ecosystem, including etcd and Flannel. We want to ensure that these pieces of software are kind of trusted and remain well supported and well loved by the community. And then the last bit is donating the container networking interface, which we built along with a bunch of other folks, but we want to see it continue to be shepherded inside of the CNCF. The other kind of thing here is that there are other opportunities to generate plugins and plugin standards for other pieces of the ecosystem. There's been a lot of talk over the last couple of days about also a container volume interface, and we'd love to see that work happen too. So these are some of the things that we'd like to do inside of CNCF as we move into the first board meeting. So with all of that said, I'd like to ask you all to join us to help build this really critical infrastructure software as open source, establish Kubernetes as this kind of ubiquitous distributed application kernel, and then also build these specifications, whether those be plugin specifications or container image format specifications that solve problems very simply. So with that, I wanted to thank you, and that is it.